Welcome back, students. In this lecture, we are going to see about single degree of freedom systems. Okay, so before to say the mechanical vibrations are nothing but oscillation of a body or particle about a mean position or in equilibrium position. So most of the vibrations are undesirable and has to be checked. So we have to understand what is the frequency of vibration and all those steps, right? So the another thing which we already know is time period of vibration, which is nothing but the time required to complete one complete to and from motion or one complete oscillation of motion. Okay, and frequency is nothing but number of cycles per unit time. Okay, it is nothing but inverse of time period. And the maximum displacement of a system from the mean position or the equilibrium position is called as the amplitude of the vibration, right? Now vibrations can be classified into two types. Firstly we have free vibration, and secondly we have forced vibration. So those vibrations which are maintained only by the restoring forces in the system is called as free vibration, and those vibrations which are caused by an periodic force externally applied is called as forced vibration. Okay, also based on damping we can say vibration can be either damped or undamped vibration. Okay, so damping basically means any resistance. It can be caused by friction or viscosity of air or anything. Okay, or by some mechanical energy dissipation mechanism. So damping is nothing but an energy dissipation mechanism, right? So the motion can be either damped or some can be undamped. Okay, so basically all vibrations are damped to some degree unless it is in a completely vacuum space or something like that. Okay, so there are free vibrations and forced vibrations, and similarly we have damped vibrations and undamped vibrations. So to classify it as, we can classify it into four types. One is free undamped vibration, secondly free damped vibration, then we have forced undamped vibration and forced damped vibration. Out of all these four, the simplest one is free undamped vibration, where there is no external force causing the motion, as well as there is no, we assume that there is no damping mechanism in the system. Okay, so about free and damped vibration we will see in detail later. Okay, now let's talk about dynamic load. So dynamic load is nothing but whose magnitude, direction or position varies with time. Okay, so dynamic load can be again classified into two types. One is prescribed dynamic load and the other one is random dynamic load. So prescribed load means beforehand only we will be knowing the variation and the intensity of the load with respect to time. So it is a, so we can carry out a deterministic analysis for a prescribed load. Okay, so random load is that beforehand only we will not know how the load is going to vary with respect to the time. Okay, for example earthquake. Okay, so earthquake is a random load. We cannot predetermine how much intensity of load will come at this much of second once the earthquake has started, right? So that is a random load. So in such cases we have to go for some stochastic analysis, or what we call it as non-deterministic analysis. Okay, so whenever this body in dynamic motion response, the deflection and stress are time variant. That means that both the deflection and the stress varies with time. Okay, so normally in a dynamic problem the dynamic load is dynamic. Okay, and a problem is said to be dynamic only if the response is dynamic. That means the vibration is dynamic. Okay, now let's see some examples of SDOF. So SDOF is nothing but single degree of freedom. So which means that we will consider only one direction of, we will analyze only one direction of motion. Okay, so here we have a simple beam and we are considering only the motion directly below the dynamic load applied Ft. Okay, similarly here we have a cantilever and we are considering only the vertical motion in the y direction. So that is also a single degree of freedom. Okay, in this case of portal frame, we are analyzing only the motion in the horizontal direction, okay, and caused by a dynamic load F of t. Clear? So free vibrations. So for every vibration to start, there should be some initial disturbance to be given. So the initial disturbance can be either an initial displacement, initial velocity, or an initial acceleration, so as to set the motion into beginning. Okay, so in order to start the motion, and the remaining things are controlled by the restoring force only. Okay, so whenever a body is disturbed from its initial position, okay, the body will continue to vibrate with a constant amplitude and a frequency, which is purely dependent on its stiffness and mass, okay, of the system. Okay, so the frequency in which this particular vibration happens is called as the natural frequency, and it's dependent only upon mass of the system, mass in the system, and the stiffness of the system. Okay, and the form in which the vibration takes place is called as the mode shape. Okay, so here we have an example of free undamped vibration. It should be noted that in a free undamped vibration, the amplitude remains a constant, as well as the time period also remains a constant. So from mean position, when the body is at mean position, we can have the particle is at 0%, and as the time varies, it goes to one extreme, positive extreme, so that is maximus, and also goes to negative extreme, which indicates by minimus. Okay, another one is example is free damped vibration. So here what happens is that along with spring and mass, there will be a damper also, which is nothing but an energy dissipating system. So in a free damped vibration, the amplitude of the vibration keeps on decreasing. So this is what the displacement curve of free damped vibration will look like. So as the time elapses, the frequency, the amplitude comes decreasing. Fine. There can be also called as something called as forced vibration, wherein the duration is caused by some external force applied to the system. Okay, so thereby what happens is the system will also try to follow the frequency of the force applied. Okay, in a forced vibration, it is important to note a term called as resonance. So resonance may be familiar to you, like it is when the external applied force frequency matches with the system's natural frequency. The amplitude increases to a very high level. So this particular phenomenon is called as resonance. Okay, so this you would have already learned in case of in physics, where you can see the example of military breaking their march steps when reaching a while crossing a bridges, etc. Right? So that is something important, resonance. So resonance occurs when the external frequency of the external applied force matches with the frequency of natural frequency of the system. Okay, so at a resonance condition, the displacements will be very dangerous and very large. Now we will see the components of vibration. So earlier we have seen already that every dynamic problem can be modeled using a spring, mass, and damper. So springs basically are used to model the restoring force. Okay, and dashpot or damper is used to model the energy dissipation occurring in the system, and also mass is used to model the inertia resistance of the system. Okay, along with this we can have externally applied force, whether if it is a externally, whether it is a force vibration, right? So this is basic model of any dynamic system. So there will be a mass rolling over a smooth surface, and it is connected to a spring as well as a dashpot. Okay, so both spring and dashpot offers a restoring kind of force. So let's assume that the previous spring system was displaced by a amount y towards right direction, okay, which means that the spring extends, okay. So the spring will try to bring it back by an amount by applying a force equal to k into y. This is a restoring force of the spring is k into y, where k is the spring stiffness and y is the distance by which the spring was stretched, okay. Also, the damper will tend to apply a damping force, which is c into y dot, where c is the damping coefficient constant and y dot is the velocity in which the body moves, okay. Already we have as force F, which was the forcing force or force of excitation, okay. So the acceleration is towards the right direction, or body moves towards the right direction. So by applying D'Alembert principle here, so in order to bring this system into dynamic equilibrium, what we have to do is we have to apply an inertial force opposing the direction of acceleration. So we apply inertial force m into y double dot, where y double dot is the acceleration and m is the mass. So mass into acceleration is an inertial force, right? So now we have this system which is in dynamic equilibrium, wherein we have four forces F, my double dot, ky and cy dot. So summing up all the horizontal forces, we have my double dot plus cy dot plus ky equal to f of t. So this particular equation is called as the equation of dynamic equilibrium, okay. So we will see how to find out the value of y dot and y double dash for a single degree of system in the coming class.